It's question show time. Your questions, my answers, as always, wherever you are on my channel. Question pops in your brain, just write it down. I'll gather them all up and I'll answer them here. Once again, we've got another special guest answerer, so stick around to the end and let's get into it. Gersum Falcon. Do Starship and Super Heavy emit greenhouse gases? This is one of the complaints that has been risen if we see like lots of Starships and Super Heavies, each one filled with methane gas launching many times a day. What is that going to do to the environment? And the plan is that the Starship and the Super Heavy use methane for the Raptor engine. And the plan is to actually produce the methane on site using this really cool process that converts carbon dioxide from the atmosphere and water into methane fuel. And if you use solar panels to actually do this, then the whole process is carbon neutral. You've got the solar panels that are pulling carbon dioxide and water. They're doing chemistry to turn this into methane fuel, and this is a very known process. So in theory, as these rockets are launching, they're entirely carbon neutral. But that's not entirely the case. We don't actually know what are the effects of rocket plumes in various stages of the atmosphere. And it might very well be that, as a rocket launches and it gets up into the higher parts of the atmosphere, then maybe it's releasing particulates that go up into the upper atmosphere. So actually more science is needed. And there's been some really interesting research that's been done to sort of think about, how these rockets launch, what they put out, what they do at the different stages of the atmosphere. And one kind of crazy idea, though, to think about it is like, say you launch a Starship with a Super Heavy and it goes off into space, you're actually taking methane, you're taking an enormous amount of methane away from the Earth, and you're sending it off into space. So in fact, if you launch enough of these things, you might actually be taking, an infinitesimal amount of greenhouse gases off the Earth and out into space. So I think the short answer is they're supposed to be carbon neutral. The long answer is we don't really know what rocket plumes do at different levels of the atmosphere, and more research is needed. So hopefully we'll find out. J.A. This may sound silly, but has anyone taken the Star Trek perspective to why we haven't been contacted by alien life yet? That's to say, we're still too primitive. They're waiting for us to stop sending junk into space that goes up once and can never be used again. They're waiting for us to become a truly spacefaring, to have vehicles that can be launched from the planetary surface, return, be refueled, and launched again. Right, so what you're referring to in Star Trek, right, this is the Prime Directive, and the gist is that they won't contact an alien species until they've developed warp drive technology. Then they're ready to join the galactic civilization. And another sort of term for this, it's called the Galactic Zoo hypothesis, that we are being watched by the aliens. They're waiting for us to get to this point that we are technologically advanced, or maybe we are sort of emotionally mature to be able to join the galactic civilization. And the problem with that, the sort of the argument against the idea of the Galactic Zoo, is it was shown in Star Trek, right? No matter how many times Kirk or Picard were aware of the Prime Directive, they broke it. They went down, met with the aliens, helped them with their problem, wooed their alien women, whatever it was, they broke the Prime Directive. And so you would imagine, like, if there are alien civilizations out there, either it is one monolithic empire that has pure, complete, perfect thought among all of them, nobody ever breaks the rules, or you've got lots and lots of different civilizations out there, and some of them may not want to interfere with us, and others may want to interfere like crazy with us. And so whenever you make one of these, like, could it be, maybe this is the reason, you got to say, is it going to be the reason for all of the aliens out there all of the time? Because if you can find one that breaks the rule, then that sort of takes that whole argument and kind of dismantles it. So whenever I hear that argument, I'm like, sure, maybe some of them do, but as long as you've got one Captain Kirk who's willing to break the Prime Directive to come down and help you with your political problems, then that argument falls apart. David Schaefer. If Elon Musk is correct and his Starship can go to orbit other worlds and land back at Earth, does that mean he's perfected the SSTO? So when you say SSTO, you're talking about a single stage to orbit launch vehicle. And this has been one of the sort of holy grails in space exploration for a long time. NASA worked on its own version called the X-33 Venture Star, which would have been this carbon fiber spacecraft that could go to space, deliver a payload, land back on Earth, get refueled, and take off again. There is the Skylon, which is under development in the UK, and there's been other ideas as well. And the problem with the single stage to orbit is really comes down to the rocket equation. Even if you could, like if the math was perfect and you had a spacecraft that perfectly worked, you would still not be able to take a lot of cargo to space because you're still having to carry all of the fuel tanks and all the extra parts to space. Now, the benefit, in theory, is that you then can land your spacecraft, refill it, and take off again very, very rapidly. But you don't get the same kind of cargo lift capability that a multi-stage rocket can do because it's just dumping excess fuel tanks and rocket engines and all kinds of stuff overboard, and it's getting lighter and lighter as the fuel is getting out of the spacecraft. So actually, what Elon Musk has done with Starship is actually better than a single stage to orbit because it is a fully reusable multi-stage rocket. Both the rocket takes advantage of all the benefits of a multi-stage rocket, but then the parts break away and return to Earth and land safely as the spacecraft carries out its mission. And so the amount of cargo that each version of the Starship is going to be able to launch into space is dramatically higher than any single stage to orbit, even if it had, perfect engineering, perfect use of mass. It's only when we shift to some other kind of fuel system, like, I don't know, solid hydrogen or antimatter or something like that, then a single stage to orbit vehicle makes sense. But if we're going to use chemical rockets, the rocket equation just kind of demands that a multi-stage to orbit rocket is actually the most efficient, most effective way. And if it's fully reusable, then they launch, they come back down, they reconnect, they launch again, they come back down, it just goes on and on and on. So that's pretty exciting. So I actually think the idea of a single stage to orbit now is kind of quaint. Federico Fuidito, how does this compare to the shuttle? When you mentioned ceramic tiles, I immediately thought about Columbia's disaster. So for those of you who weren't aware, of course, the Space Shuttle Columbia was the space shuttle that was lost as it was coming back through the atmosphere to re-enter. And what NASA learned was that as the shuttle was going to launch, a chunk of the insulation on the main shuttle tank fell off and came down and smashed into the leading wing of one of the sides of the shuttle. And then the shuttle went up to space and did its mission. Then as it came back down through the atmosphere, it's a very hot process. Hot gases were, consume the outside of the space shuttle. And because this chunk of insulation had knocked off a chunk of the space shuttle's tiles, these hot gases were able to get inside and destroy the space shuttle, and all of the astronauts were lost. So it was a real disaster. Now, in theory, there are more advantages with the Starship. The first thing is that it's being made of stainless steel. The shuttle was made of aluminum, which is not so durable to this high heating. And so because of that, it doesn't actually require the same amount of shielding that, say, the space shuttle did. With the space shuttle tiles, they were very thick tiles that needed to be carefully inspected after every launch. And so because the temperature that stainless steel can handle is higher than aluminum, the amount of shielding and the complexity of the shielding, in theory, is going to be less. But really, this is where the rubber hits the road, where the ceramic hits the road of this entire process, is that we're probably going to see the Starship make its vertical hop. That's going to work great. But the question is, when Starship goes to space and it comes back down through the atmosphere and it's going from 28,000 kilometers per hour to zero, and it's having to go through all that atmosphere and it's got all that heating, will it be able to handle it? Will it be able to make it through? And will it be able to do it without requiring a tremendous amount of refurbishment? Or will the thinner ceramic tiles that SpaceX is planning be able to do the trick? Will those air brakes be able to keep the ship perfectly oriented as it slams back through the atmosphere? So they've done the math. They think this is going to work, but I think that we're going to see that a pretty big gap between when they start trying to do orbital launches to when they're comfortable and they feel like the whole process is safe enough that human beings can go on board. And so that's, if I was to make my guess about which part of this process is going to take longer than anyone expects, I think it's going to be that. But we will find out. Murillo Klein. Hey Fraser, great content as always. I have a question. How will asteroid mining companies know which asteroid is worth mining? Do we currently have demand for any specific elements and materials out there? Thank you. Before you can actually mine the asteroids, you need to know what those asteroids contain. And actually, was one of the plans of the company Planetary Resources. And I think they've fallen into some financial hard times now. They got picked up by a Luxembourg company, but their plan was to send a prospecting robot, a prospecting spacecraft out there into the solar system to be able to actually understand what's on these different asteroids. And so you send a small ion-powered spacecraft, it flies out to an asteroid, scans the asteroid, understands the chemical constituents of it, tries to detect if there are some, more valuable elements on it, and then reports that information back to Earth. When you think about, like, say, OSIRIS-REx or Hayabusa 2, which are both orbiting asteroids right now, they're scanning them in incredible detail, they're understanding the mineral compositions, things like that. So just imagine hundreds of those flying around the solar system, analyzing all the different asteroids. And there are a bunch of materials that are actually incredibly rare here on Earth, but are a little more common out there in space. Some good examples are some of the more rare elements like iridium, palladium, some of the heavier metals, which are really expensive here on Earth. And so you could imagine some future factory flying to an asteroid, dismantling it, pulling out all the heavy elements, sending them to Earth. One idea is you just sort of weave it into this great big, like, steel wool ball, and then you just drop it through the atmosphere, and it can actually survive. It sort of has such a high surface area that it'll slow down and just, make it through the atmosphere without all burning up and turning into palladium gas. So so it's just going to be a whole bunch of prospecting first to understand what these asteroids are made of, followed up by missions to harvest the resources. Charles Uwakwe. Hey Fraser, my question for you is, in a binary star system, what could possibly cause the stars to collapse into themselves? And if this happens, what happens to the planets that star system has? I'm trying to understand the question a bit. Now, you're saying, like, what would cause the stars to collapse into themselves? Are you talking about, like, gigantic, supermassive stars, like, that are many times the mass of the sun, and they collapse in on themselves and they turn into supernovae? They'll do that just normally, right? Like, if you've got enough star with enough mass, then it has a very short life, and then it uses up all the material in its core, collapses as a black hole, detonates as a supernova, and if it had a binary companion, then that star is gone. If you're wondering like how they can form, like, right from the beginning, how they could actually form together, and it's thought that it works very similar to the way a regular planetary system works. But instead of having, say, one star, like one sort of center of the mass at the heart of a newly forming planetary system, you've got, a larger chunk, and as it's spinning really rapidly, it can spin out into two pieces that then are orbiting around each other. Or maybe you've got sort of two blobs of gas that are sort of farther away, and they are orbiting around each other, and then they both turn into stars, and they just continue to orbit around each other. So there's different configurations. But I'm going to show you a photograph now, which is brand new, and this was taken by the ALMA Observatory, and this is an image of a newly forming binary star system. So you can actually see the two stars and the disk of dust and material around it, and that's where the planets are going to form. So at some point down the road, you're going to have two stars orbiting around each other and a planetary system that is going around both of those stars. And this is the first time, I think, that we've ever seen a photograph of this actually happening, which is pretty cool. Jeff Mathers. Talking about tidally locked got me thinking, can tidally locked planets have a tilt? If so, wouldn't the polar regions have day-night cycles? Yeah, this is a great point. And so, we don't know of any tidally locked planets in the solar system, but we do know of tidally locked moons in the solar system, and the best example is the moon. And the moon is does not have the same axial tilt as the Earth does, and it doesn't even orbit necessarily within our plane. It just shows the same face to the Earth at all times. And so one of the cool things about this is that we can actually see more of the moon than we would normally be able to see. If the moon was perfectly flat in its orbit around the Earth compared to the sun, if the moon was perfectly if its axial tilt was 0 compared to the Earth's axial tilt, if it was in a perfect circle, then the moon would always look exactly the same to us from our perspective. But I'm going to show you a video now, and you can see how the moon actually appears to kind of wobble and show us more of its face. And what you've got is actually the moon is on an elliptical orbit around the Earth, and so it shows a little bit more of us as it gets closer and farther. And also, because it doesn't have the same axial tilt as us, we're able to kind of peek above and below the moon as it goes around on its once a month orbit around the Earth. So you would anticipate that planets from other stars would have similar configurations. Speet spoot. The moon would be a great place to look for Martian meteorites. The problem with the moon is that it doesn't have any atmosphere, and so as meteorites strike the moon, they're coming at their full velocity. They're going at, say, 5 kilometers per second, and they smash into the moon and they just vaporize. They cause a crater, and the debris, the ejecta, lands around the whole area. A better place to look for meteorites is actually Mars, because Mars does have an atmosphere. And so as meteorites pass through the atmosphere, they get slowed down and they land on the surface roughly in one piece. And in fact, various rovers from NASA have discovered meteorites, metal meteorites on the surface of Mars, and we don't really know where they came from. They probably came from the same place the metal meteorites that we have here on Earth came from. So to have a place that would be good at catching meteorites, it needs to have an atmosphere. Venus is probably like one of the best places. There's probably tons of meteorites down on the surface of Venus, but I don't want to go try and get them. Adam Shupp. Can the Hubble Space Telescope record video if someone wanted, or can it only take individual pictures? No, the Hubble Space Telescope doesn't do video. What the Hubble Space Telescope can do is it can take exposures. So anyone, if you ever used a camera and you take pictures, you can set the amount of the exposure time. On, my camera, I can take a picture that's 30 seconds exposure, or I can take a picture that is 1/4000th of a second. And so the shortest exposure time that you can have on the Hubble Space Telescope is 1/10th of a second. And so if you wanted to make a movie, you would take a whole bunch of 1/10 of a second pictures and then you would stitch them together. But the problem is that for astronomy, you don't want to take short exposure pictures. Only when you've got something bright like the moon or the planets does it ever make sense to take short exposure pictures. Like maybe they're doing that with, say, Saturn or Jupiter. They're taking a 1/10 of a second exposure. But for pretty much anything else, you want long exposures. You want exposures that are minutes long, hours long, days long. Charles the Bandhammer. Hey Fraser, what can be done to stop a runaway greenhouse effect? For instance, would we be more worried about volcanic eruptions or CO2 emissions that we are dumping into the atmosphere? So right now, human carbon dioxide emissions are dramatically higher than volcanic emissions. They're higher than an asteroid hitting the Earth, so they're quite high. The good news is we can't cause a runaway greenhouse effect here on Earth, that even if we pumped out mountains and mountains of carbon dioxide and made the planet unlivable for human beings, we would all wipe ourselves out, and then the planet would reset, and then it would go on about its time for another 500 million years. So we can't turn Earth into Venus. We don't have that in our power. We can only turn Earth completely unlivable and wipe ourselves out. You need something a lot more dramatic, and it really looks like what happened with Venus is the whole planet just turned itself inside out. Imagine that, right? Instead of it having plate tectonics, which moves the plates around on the Earth, the whole planet just flipped inside out, volcanism everywhere, and that shut down the carbon cycle and then dumped enough carbon dioxide to make an atmosphere. Remember, it's 90 times, if you're standing on the surface of Venus, you're experiencing 90 times the atmospheric pressure than you are on Earth, and we can't dump out that much carbon dioxide and not just, all suffocate. So don't worry, we're only going to wipe ourselves out, and a lot of species on Earth, we're not going to destroy the Earth. Rachel Quinnell. If telescopes allow us to see distant galaxies, but as they were in the past, say the redshift, how do we know what they are currently doing? If it shows light from billions of years ago, then couldn't that reflect it from the Big Bang when there was such a great expansion? All right, to answer your question, I brought in a friend, Tony Darnell from Deep Astronomy, and he's going to answer your question.
Those are good questions, Rachel, and I'll start with the first one. Einstein's speed limit, that nothing can go faster than the speed of light, is both a blessing and a curse, and it has a lot of implications on what we can know about the universe at any given time. Now, it's a blessing because it means that in a universe that's almost 14 billion years old, when light finally does reach the Earth from all corners of the universe, it's been traveling a long time, and we are looking at how things were when the photons left. This means we're looking back in time, at a time when that light left. And the further away something is, the earlier we can see in the universe because of that. But it's a curse because in a universe that's almost 14 billion years old, we can never get direct information from far away in any kind of timely manner. We cannot know, for example, when we look at a galaxy 1 billion light years away, what that galaxy is like right now, a billion years later. We can only see what was happening when that light left the galaxy so long ago. It's a snapshot of the past. So what it's doing right now, we'll have to wait a billion years. Now, to the second part of your question, if it shows light from billions of years ago, then couldn't that reflect it from the Big Bang when there was such a great expansion? Now, if I understand your question correctly, you're asking if information from the early universe can be given to us in information from the Big Bang, which was reflected somehow during a period of rapid expansion. I think the answer to this has to be no, because all events seen early in our cosmic history are still bound by the speed of light, and what happens later as the universe expands cannot be reflected from an earlier period, say the period of cosmic inflation, which I have to say, right now, astronomers include it as a way of explaining current observations, but it hasn't really been confirmed in any serious way, and many people don't think it explains anything anyway. But that's a topic for another video. I will wait. So Rachel, you've hit on something that's really fascinating to think about. What is the universe like right now, everywhere? Except for those things really close by, like the nearest stars, we simply don't know. And even then, the information is dated by several years, like 4.5 years in the case of Proxima Centauri. And a galaxy observed 1 billion light years away looks to us as it did 1 billion years ago. And since then, all kinds of really cool things would have happened. So it would be awesome to see what that galaxy is like right now. And to make things even more complicated, the universe has gotten a lot bigger since then. To see what that billion light year away galaxy is like right now, we'd have to wait even longer than 1 billion years to see what it's like today. Why? Well, the universe expanded and got bigger in those last 1 billion years. So we need to wait 1 billion years for light to travel the distance it is from us now, plus an additional distance that the universe expanded during that time that it's been expanding. I know. So sadly, the distant universe, as it is today, will always be closed to us. Based on the current values of the expansion rate of the universe, astronomers estimate that the size of the cosmos, the observable horizon, is around 93 billion light years across. At the edge of this horizon are photons that left the universe some 13.5 billion years ago. The cosmos got really big during those years, and in another 13 billion years, some of those early galaxies will be forever lost to us. The speed of light limit, coupled with the sheer vastness of the universe, means that what's going on in the distant corners of the heavens will always be closed off to humanity. So thank you, Rachel, for an awesome question. I want to thank Fraser Cain and Universe Today for letting me hang out with the big boys. And thanks to all of you for watching. And whatever you do, keep looking up.
Thanks, Tony. That was wonderful. I highly recommend, if you haven't already, subscribe to Deep Astronomy with Tony Darnell. He's got mountains of really amazing astronomy content, lots of great live streams, a lot of behind the scenes conversations and interviews with people working on some of the coolest observatories. So if you are into astronomy, definitely follow Deep Astronomy. And then the other thing that Tony does is he is one of the co-hosts of the Space Junk podcast. And I've been a guest on this podcast a couple of times, talked about the Fermi paradox, talked about my thoughts on UFOs and aliens and things like that. So go and subscribe to the Space Junk. I'll put links to all that stuff down below. All right, those were all the questions this week. Thanks everyone who jumped in there. Sorry the wind was so strong. I will, as always, question pops in your brain, write it down, I'll gather them up, I'll answer them here. I'll see you next week.